Hi there, welcome to a new physics lesson filled with adventure and discovery. Today, our topic is uniform circular motion. And my job is to kind of introduce you to that. So far, we've been talking about, we've been just trying to describe motion in our universe, and we've only been going in straight lines. But how do we describe it when it's moving in a curve or a circular type of motion? That's our topic for today. And so let's jump into it. Uniform circular motion we can describe is any object that moves at uniform speed in a circle of constant radius. So as long as you're moving in a constant circle at a uniform speed, we would say you're going through what we call circular motion. And so we can state also that uniform circular motion is what we call accelerated motion. That when you're moving in a circle, so let's say we were to spin around in a circle, we are actually accelerating while we are spinning around in the circle. And so why is that? Why do you think that is? Yeah, why do you think that is? Well, remember that when we're talking about acceleration, the definition of acceleration is a change in velocity. So if we are spinning in a circle, because if we're to draw our velocity vectors, you would start to see that something spinning around in a circle wants to actually, and if let's say we're to spin around, and I'm holding my computer here and I were to let it go, my computer would want to keep going straight or in a straight line, but because I'm holding onto it, I am actually keeping it from accelerating and just keep going in a straight line. And so because we're changing our velocity vector at every interval of our circle, we can say that it's accelerating. And so a lot of people would say, oh, whenever, like, imagine you're on a merry-go-round. And I don't know how long it's been since you've been on one, or maybe you've never been on one. They don't have too many of them anymore. But when you're on a merry-go-round, or even on a roller coaster that spins around really fast, you start to move. Which direction you start to move in your seat, or even if you're in a car turning, right? You start to be pulled or pushed towards the outside rim of that seat, or towards the outside of the car, opposite of the direction that you're turning in. So a lot of people would describe this as a centrifugal force, and hence we have these devices called centrifuges that are used to separate compounds based on their size. And the centrifuge spins really fast, and it causes things to spread out and get trapped towards the outside of the machine. And so we would say that, oh, there's a centrifugal force that kind of pushes us in the opposite direction of where we're turning, or if we're spinning in a circle, it pushes us towards the rim, outward of this orbit that we're circling in. However, centrifugal force is actually a myth, and here's the reason why. And a lot of you might be like, what? It's a myth? Well, when you're spinning around in a circle, or let's say you're in your car and you make a sharp turn, your body, because of Newton's first law of inertia, your body wants to continue moving in the same direction that it was, which is straight. But when you turn, because you're moving straight, because you're changing in direction, your body wants to move in that new direction, and hence you feel like you are being pushed or pulled towards the outside. But really, it's your body just wanting to continue its path of motion. And so Newton's first law is more of a description of this force. There actually is no centrifugal force that's pushing you towards the outside of the car. Although you feel like it, it really doesn't exist. It's only your body's inertia. And so here, notice that if you're in a car, right, and you're driving and you make a turn, the car and your body wants to keep moving straight forward. But if the car turns and moves along this curved line, your body will be pushed. It's going to want to keep going forward, and hence it's going to be pushed towards the outside of this car. It's going to gravitate towards the outside of the car. So you feel like you're being pushed outside, but really you're just moving straight ahead in the direction that you were moving in a moment earlier. Now here's an interesting thing, that when you turn in a car, in order to make this turn, or in order to make this curve line, or even when you're spinning something, let's say you're spinning like a weight that's connected to a rope. Okay, in order to continue in that circular motion, there needs to actually be an acceleration or a tension that keeps you in that orbit. Okay, so here's an example. Your inertia resists that curved acceleration, and so that's more of an application of Newton's first law rather than a force. So the acceleration vector is always at right angles to the velocity. Like I said, there has to be something that's keeping you in orbit. The acceleration has, in order to keep moving in a circle, there has to be something that's pulling you towards the center. And so we have a name for that. We call that centripetal acceleration as opposed to centrifugal acceleration. So centrifugal acceleration really doesn't, or centrifugal force doesn't exist. Rather, we have something that keeps you in this orbit called centripetal acceleration. Okay, and so this acceleration, the centripetal acceleration, is always going to point towards the center of the circle, and this is in order to keep you in this circular orbit. Otherwise, your velocity is going to take you straight up. And hence, if you're swinging something and you let go of it, it's going to go in that straight path, that straight velocity vector of which you let go. Okay, and so here's our equation for centripetal acceleration. Centripetal acceleration is our velocity squared divided by our radius in meters. So we're going to be measuring our radius in meters. Our velocity is what we call tangential speed, because it's kind of the line of a curve. Okay, it's kind of that that straightaway line based upon this curve, tangential speed in meters per second, and we take the square root, we square it divided by radius to get our centripetal acceleration. Okay, so centripetal acceleration will always point towards the center. When we're talking about centripetal force, that there has to be a force that keeps you pulled towards the center. We can expand it to this. So our centripetal force, Fc, is equal to our mass times our centripetal acceleration, in which if we substitute what we just found for centripetal acceleration, velocity squared divided by radius, we have this beautiful equation which is on your equation sheet. Okay, and so applying Newton's second force, we can calculate for our centripetal force. Now, so here's some other side things to mention before we move on from this topic. That centripetal force is not a unique type of force, right? It follows F equals ma. It can cause a net force, which keeps you changing directions in this circular motion. Okay. And the centripetal force always arises from other forces. It's always a tension force, or it could be a friction force. And so here's some examples of that. When you're turning in a car, there needs to be something that causes you to turn in that circle. And in this case, there's friction that's holding your car and causing your car to be able to move into this circular motion. And so when your wheels are turning, this friction allows it allows there to be a centripetal force that allows you to turn. If there was no friction, your car would not, if your car was somehow able to start moving, it would be unable to turn. Even if you turn the steering wheel, it'll just keep going straight on. But because there's friction, we're able to turn your car. Same thing with if you have something that's tied to a string. That string is now your centripetal force that's causing this tension of the string, causes your bucket to be able to spin around. And lastly, one of the most important examples, Newton's theory of gravity, right? It holds moons in orbit. It also causes our planets to orbit around the sun. Okay, and so in some cases, it could be a combination of both. If we have a mace here, so we have a weight on a string moving in a vertical circle. So if we're moving it like this, where the circle is like that, we're spinning it sideways, or the spin is vertical, then the centripetal force could be a combination of the tension of the string as well as the gravity. So it could be a combination of both forces. Okay, so we see this in roller coasters a lot when we're moving in loop-de-loops. Okay, there's a centripetal force that acts upon you when you're upside down. And that force is a combination of the normal force of the track as well as gravity. So that's our introduction to circular motion. Thank you so much for joining us, and we'll see you next time.